Hi guys, so I'm gonna go over the review for exam number 2. So it's for the calculus-based class. And the topic is Newton's second law and how to apply Newton's law. So I'm gonna skip conceptual questions and I'm gonna focus on the numerical questions. So let's review simple problem here. Question A is just find the acceleration in both cases. So just before going over those two problems, if an object is at rest, so here you have a block, you have two forces acting on it. So you have the weight, okay, so that would be the weight. Magnitude is mg. So it's pulling down, and because it's pushing on the ground is going to push back. Okay, and I should do that better because you see the magnitude of the forces will be the same. So this is called the normal force. Normal because it's perpendicular, not because it's some forces are abnormal and some forces are normal. Normal means perpendicular. So if you have a bathroom scale, so if you put a bathroom scale here, okay, so I think that will be one of the conceptual questions. So you have a bathroom scale here, then you're going to read the real weight. Okay, so the normal force is actually the reading of bathroom scale. So in that case, it's the real weight that you're going to read on the bathroom scale. Okay, so what's going to happen in this case here? So I don't know if I should so in this case here, so what are the forces acting? So in that case, you still have the same weight, but now this force here, we can call that there is a string, so that will be a tension. Okay, you see it's doing two things at the same time. It's pulling the block forward, but it's also lifting the block up. So it means now it's not pushing as hard on the ground. So that means that you have a normal force, but the normal force will be a little bit smaller. So you see that force here has two components. Okay, so it has a x component, so that will be how much of the tension is along the horizontal. So I'm going to call that x. And you have a y component. So for vectors, you always go from the tail to the head. So you run and you rise, or you run and you fall. So in that case, you rise. Okay, so the component here will be t sub y, which is the same thing as here, right? So it has two components, x component and the y component. So the y component is lifting the block off the ground, and the x component make it move forward, and we suppose there is no friction. Now, if you insist, we can always make a free body diagram. So in that case, you see you have this vector here, t, you have a weight down there, and you have a small normal force here. So that will be the free body diagram. Now, conceptual question. If you have a bathroom scale here, so if you put a bathroom scale like I did here, so you put that on the bathroom scale, but it will be weird, right? But because you are lifting up, you see the the normal force is less, so you will read less on the bathroom scale, right? If the bathroom scale will slide with it and they stick to each other. So the normal force is what we call the apparent weight. So it will be less. Okay. So anyway, let's go back to the free body diagram. You can also draw here the components. So the X component, you see, does not have anything to balance out. And you have the Y component here. Okay, you can do it here, you can do there. And you see that along the Y-axis, nothing is happening. So up equals down. Okay, so you can say along the X-axis, so it's along the horizontal X-axis, you see that T sub X is to the right, so this is positive here, will be equals to the mass times the acceleration. And along the Y-axis, okay, they kill each other out. So it means that the normal force plus the Y component of the tension will be equals to, so this is the scalar. Here the weight is mg. Okay, so X component here, so here you have a 30 degrees. It's in the first quadrant, so I don't have to think about trig. First quadrant, X component here, and the angle is with the positive X-axis, so it's always cosine. So it's going to be T in magnitude, so it's 10 cosine 30 equals the mass. I think the mass is 2 kilograms, which is 2 times the acceleration. Okay, so acceleration will be 5 cosine 30, and so cosine 30 times 5, which is 4.3. So I don't know if you want to pay attention to the significant figures. I don't know, maybe 2, so 4.3 meter per second. Okay, so that will be the acceleration this way, because there is a net force. So here you apply Newton's second law. Okay, so the net force equals m times the acceleration. And you have to divide into X-axis and Y-axis. So this one, it's the same idea. So you see it has also 2 components. So same thing here. You have the weight for sure. But you see now this push here is doing 2 things. It's pushing forward, but it's pushing into the ground. So now if you have a bathroom scale, it's gonna be more weight, right? You push harder. So that means that the normal force in that case here will be larger than the weight. Okay? Because if you look at the components here, you have one component down, T sub Y, and one component forward. Okay? And of course, this is parallel to that, so that's going to be also 45 degrees. So if you insist, we can always have a free body diagram. So you have a big M here, and the weight is less, and you are pushing. You always attach the vector to the origin. Okay, so vector can be cut and paste anywhere you want. So now you have here tension. Always attach the tail here to the origin, and this is 45 degrees. So it has, again, two components. One component is making the forward motion happen and is responsible for the acceleration, and it's also pushing down. So there is also an acceleration in this direction. Okay, so this will be cosine, right? So along the x-axis, so that was for A. For B, along the x-axis, now I have t cosine 45 equals mass times acceleration. So 10 cosine 45 equals 2 times acceleration. So the acceleration is 5 cosine 45. Okay, so 5 cosine 45. So 3.5. So the acceleration is 3.5. So that's for number B. Along the y-axis, now we have the normal up, okay, plus ty is up, so t sinus 45 equals the weight. Okay, so along the y-axis, I can say up equals down. They kill each other out. And you see that the normal force is not as large. You can compute it, okay? So if you take G equals 10, so that will be less than the weight. The weight is supposed to be 10 times 2 is 20, so it's going to be 20 minus something. Okay, because you don't push us hard on the ground. Okay, so the next question is, what's going to happen if now you have an acceleration? No, if you have friction. I'm going to save this. So now if you have friction and the coefficient of friction, so that will be kinetic friction, is 0.1. So if we again look at the forces, so along the x-axis, you still have the x component. Along the y-axis, you still have the y component. You have the weight, and the normal force is smaller than the weight because you see it's balancing out the weight and you are lifting up. And now you have a frictional force, okay? So we want to make sure that frictional force is smaller than that Tx. Okay. Otherwise, if it equals to, it's moving at a constant speed. If we get a number less, that means it's not moving. Then we have to use the static friction. So let's do all the equation. So along the y-axis, we have up equals down. So we have the normal force plus up. We see the y component, it's a sine, so it's going to be 10 sine 30 equals down, which is mg, and the mass is 2 kilograms, and we take g equals 10. So that's going to be mg, which will be 20. Okay, so that will be my first equation. Second equation, the definition of frictional force. Friction between both, okay, depends how hard it's hooking up with the ground, how hard the object is hooked up to the ground. So of course it's going to depend on the normal force, right? So if the normal force is small because you are lifting up, you don't have that much hooked up. So the normal force is in magnitude, okay, it's the frictional force times, no, sorry. So by definition, the frictional force equals the coefficient times the frictional force equals the coefficient times the normal force. Okay, so how hard you push on the ground. So that will be your second equation. And then you have the x-axis. So forward, so you have that force here, which is 10, and that will be cosine 30 e minus, okay, because this one is opposing. So the idea, you try to take always the acceleration in a positive direction. So acceleration is this way. So I don't have to worry about the sign. Minus the frictional force equals mass, which is 2 times the acceleration. And that will be the third equation. So to have the acceleration, I need to find the frictional force. To find the acceleration, frictional force, I need to find the normal. To find the normal, I go back to 1. So from 1, I have that the normal force equals 20 minus sine 30 times 10. So that will be, so this is 5. So that will be 15. Okay. Number 2, we use equation 1 in equation 2. So we have the frictional force equals 0.1 times the normal force, which is 1.5 Newton. Okay. And that equation here, you can call that equation 4. So equation 4 into equation 3. So you have 10 cosine 30 minus 1.5 equals 2 times the acceleration. So it's going to be 10 times so 10 times cosine 30, okay, minus 1.5, okay, and you divide by 2. So it's 3.6. If you take two significant digit, 3.6, sorry. Okay, so if you can do the same thing with the other one. So if you take the same thing with the other one, I'm not going to solve it. I'm just gonna lay out the equation. I'm gonna save that. So here again, it has normal force larger than the weight, and you have the weight larger Z. Okay, so this is the weight here. And then here you have the push. I don't know why I call it T. It should be a push, right? But it's fine. Okay, so then you have three equations. Up equals down, so y-axis. You have up equals down, so you have the normal force, which is up. And down, you have the 10. Down will be a sine. This is down. Okay, so this is that side. So it will be a sine 45. Okay, so that will be your down. Plus I plus the weight, which is 20. Okay, so up you have the normal force, and down you have that y component here plus the weight. Okay, so you can find the normal force. That will be your first equation. So it's going to be 10 the sine 45 plus 20, which is 27 Newton. So you see, before we found 50 Newton. Now it's more because you are pushing on the ground, so the ground push back on you more. And then by definition, the frictional force equals the coefficient times the normal force. So it's going to be 0.1 times 27, which is 2.7. Okay. Now along the y-axis, we use Newton's second law, ma. So it's that push here. So it means T cosine 45. Okay, so this is 45 equals a minus. Okay, so forgot to draw the force here because you have friction opposing the motion. So it's going to be T cosine 45 minus the frictional force. So this is 10. So this is 10 Newton. 10 cosine 45 minus 2.7 equals 2 times the acceleration. Okay, so you can do the math. So 10 cosine 45 minus 2.7. Okay, divide by 2. So 2.2. So it's a larger, it's a smaller, so it's smaller acceleration because you are pushing on the ground. Okay, so it's more friction. So I'm gonna save that as well. Last question. Okay, so last question, very important for the test. What's gonna happen if now you have, so in that case, what's gonna happen if now you are also pulling in this direction? So there was a force here, 20 Newton. Okay, someone is pulling and this one is kind of pushing. So again, you have two components here, y, and we say no friction. Okay, we're not going to make it more complicated. So along the x-axis, you see that 20 minus, that was in the other case. So, anyway, it's good. 10 cosine 45 Okay, so this one is helping, and this one is helping. Sorry, so it should be a plus. Okay, equals 2 times the acceleration. So now we have a helper. Someone is helping plus 10 cosine 45. Okay, and divide by 2. It's about 13.5. Okay, so that was from number 1. So this one is the next one, and it's a easy one. The only challenge is just to be able to make a drawing of the situation. So it says it's and to remember kinematics equation. Okay, so that comes from the book University Physics. So it's your textbook, and the author are Young and Friedman, I think. So it's a very good book for calculus-based classes. So anyway, you have to read first. So you have a bottle and a smooth table, but smooth, and you have the weight. Smooth doesn't mean it's frictionless. It means that if there is frictional force, it will be the same all along. That's what it means. So she shoved the bottle, and it says initial velocity is 2.8 meter per second, and it's going to stop. Okay, so it's going to move. So that at t equals 0, that's the initial velocity. So I'm going to call that initial velocity. And of course, you want to pause the video. Ta 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 ta. Okay, so it's moving, but it's slowing down. So it has a smaller velocity because you have a frictional force here. Okay, you also have, of course, the normal force is up and the weight is down. So in that case, weight equals frictional force, right? Because there is no force at an angle, like in the previous example. And at some point, it's going to stop. So at that point here, that will be the final moment. You can also, it's a nice review for kinematics. You also have a displacement, delta x. Okay, so everything is in the drawing. Okay, so this will be the positive direction. And we see that in that case, the acceleration is, you have an acceleration this way. Why? Because the frictional force is in this direction. Okay, so we have we can take this way to be positive if you want. So that way you have positive here and negative there. I like to take the positive always in the same direction as the acceleration, but it's very simple to apply. F equals ma. So this is the force applied. So the frictional force equals mass times acceleration. So we don't have the acceleration. We do have the force, and that's what we are looking for. So direction we already have, right? So in that case, it will be opposing the motion. So that will be the equation I'm going to use. Actually, you know what? I'm going to, for kinematics, so now I'm going to use kinematics. And if I want to use kinematics, maybe it's this one is easier. This one doesn't really matter because I can just put down the magnitude. I can put here, okay, let's stick to plus to the right and minus to the left, and then we will use this one. So first we're going to use kinematics. I just have to be consistent. You could use the opposite, but I just have to be consistent with the sign. So kinematics, it's going to give me the acceleration. And you see that the final velocity equals 0. And I'm missing something here. Delta x is 1 meters. So 1 meter. So I can use the equation final square equals initial square plus 2 times acceleration times delta x. You could have done the opposite actually. But anyway, final is 0, initial square plus 2 times the acceleration. Now the displacement here is positive. If I stick to this, so you have the acceleration will be minus 2.8 squared over 2. Okay, and you get 2.8 squared divided by 2. So you get an acceleration of 3.92. I'm going to keep the decimal because here I have 1, 2, 3. Here I have 2. So maybe I should keep only 2. But anyway, you can say minus 3.9. But because you have other computations coming up, so you can keep that number here. Then I go here, and the kinetic frictional force equals the mass, which is 0.45. And here I have a minus 92. Minus 392. So times 0.45 and minus 1.8. Okay, and no, I did something wrong. I don't know why I divided by 2. So 3.92 times, oh, no, that's correct. So minus 1.8, okay? So the mass is 0.45 kilograms. Okay, and then you can keep 2 significant figures because here you have 2. So it's negative if to the right is positive. Okay. So this one is just reviewing pulleys and mechanical advantage. So I got this one from the web, from internet. And so the first thing you want to know is, let's define a system. Okay. So when it's a little bit confusing here, the first thing you want to know to define is your system. So you put all this like in a bag. So that's going to be your system. And then, so this is your system. It's like in a bag. The bag has a mass of, so you see here, that will be the weight. So 10 kilogram about. Okay. So G equals 10. So you have 10 kilogram. And once you have defined your system, that's your bag. So you put everything in a bag. What are the forces acting on that? So you have 100 Newton down, and then you have one string up, one string up, one string up, one string up. So you have 1, 2, 3 forces pulling. 1, 2, 3, 4. And what else do you see? That it's the same string. Okay, you don't have different string. It's the same string. And if the string does not have mass, and if the string cannot be stretched, so the rule is that the force is the same all along the string. So that's going to be a T, that will be the same T, that will be the same T, and that will be the same T. And that same T here, that T here will be the same as this one. So this here, that weight is called the load. That's your load. And here, that will be the effort. Okay, so we have T equals the effort. Okay, so it's the same string. So this here will be the same as that T here. Okay, so then you can use up, it's in equilibrium. Up equals down. There is no acceleration. So 4T equals, that's 100 Newton. So T equals 25 Newton. So here the effort is 25 and the load is 100. So the mechanical advantage will be the effort or the load, the load over the effort, that will be 4. Okay, so it means you are 4 times stronger. Okay, it's a machine, it makes you 4 times stronger. But there is a price to pay. If the effort here move by a distance of 10 centimeter, okay, that will be the work done against gravity. So the price to pay is that you have to pull over 40 centimeter because it makes you 4 times stronger. Okay, it makes sense. You can use conservation of energy. Okay, so energy in equals energy out. Energy in, it's energy in transfer. So here it will be force times the distance. Okay, so energy in, if it is U, so effort times the distance, 1 equals the load times distance 2. So if you decrease the effort, it means it's easier, the distance has to go up. So that's the rule. But the only challenge here is really to define the system. So this one is the next one. So the first question here, it's sliding along the ramp and there is no friction. So for inclined plane, you can memorize that, first of all, you always take the x-axis here, okay? Positive could be in this direction or it could be the opposite direction depending on the acceleration, but the x-axis is always along the plane. And then of course, that means that the y-axis is always perpendicular. The other thing that you have to memorize is that the normal force, so normal is perpendicular to the surface. So normal force always goes from the surface or the ground to the system that you are looking at, right? So in that case, the system is the sled plus the people here sliding. So where is the normal force? Always from the ground or the surface to the system. And it has to be perpendicular to the surface. So that means the normal force is going to be here. Okay. And the weight, okay, is always straight to the center of the earth. So the weight in those cases is always straight down. Okay. The other thing that you have to memorize with inclined plane, that will be the angle here. The angle is 40 degrees. Now, one thing I already told you is that when something slides on an inclined plane, just no friction, just sliding down, you see the acceleration will be diluted. It will be the acceleration due to gravity, but it's diluted. Okay. That's something to keep in mind. That was the experiment done by Galileo. Okay. There is a dilution of gravity, but you can always, retrieve that. So let's show that. So you see here you have the y component of the weight. That's going to be the y component of the weight, and that will be the x component of the weight. So it's the x component of the weight, so how much weight there is along the inclined plane. This is the one making the system move forward. This component here is pushing on the surface, balancing out the normal force. So you can even memorize that the x component of the weight is always mg sine. Okay, because that will be a sine. Yes, it's the opposite. Just memorize it. The x component of the weight along the inclined plane is mg sine. So that will be along the x-axis. Then you use Newton's second law, F equals ma. So that's going to be m times the acceleration. So the acceleration will be, so if you take g equals 10, so it's going to be 10 sine 40. It's about 6.4. Okay, so you can keep two digits if you want. And along the y-axis, you see, along the y-axis, you see that the normal force will be equal to the y component of the weight, which is mg cosine 40. Okay, so the force, which is what? The mass is 100, so 1000 cosine 40, which is 1000 cosine 40, 766. Okay, but here they just want you to find the acceleration. That comes also from your book. Okay, it's very important to see, you see to tell the source, so university physics. Okay, now there is friction, so now it's not moving. Okay, so we take the same thing, but it's not moving. Okay, so it's the same problem, but because there is friction, then it doesn't slide anymore, right? So what are the forces? Still the same. So still, you still have to take always the x-axis along the inclined plane. That's going to be the y-axis here. And then that will be the weight down here, mg. That will be the normal force perpendicular to the ground, from the ground to the system. So that's going to be the normal force here. So again, you have two components for the weight. The one that make it goes down. Okay, so the y component here. And you always have that angle here. So if it does not slide, that means on the x-axis, you're going to have a force here, which is the frictional force, and that will be equals to the x component of the weight. So if it's not moving, it has to be static friction. Okay, so along the x-axis, now we can say that right equals left, so it's in equilibrium and it's at rest. So that component here is always mg sine, so we have mg sine equals the static friction. It's not the maximum static friction, it doesn't have to be. So for example, if you increase the weight, the static friction will increase until it's reaching the maximum one. So the maximum static friction equals this, but otherwise you cannot use this equation if you didn't reach yet the maximum static friction. So to make it slide, you can increase the weight or you can increase the angle here, the slope. So anyway, so that's going to be 1000. So 1000 sine 40, and you get 1000, and then it's sine 40, which is 643, about 643 Newton. Okay, so that will be your frictional force, and they balance each other out. Now, if you have a bathroom scale, so if you use a bathroom scale, okay, so I'm answering this question here. If you use a bathroom scale, it depends, your reading will be the normal force, right? So normal force is always the apparent weight. So how hard you are pushing on the balance scale, the bathroom scale, and how hard is pushing on you. So in that case, you have up equals down. Okay, up equals down. So you have mg cosine 40 equals the normal, right? So the bathroom scale, okay, it's gonna read 766 Newton instead of 1000 Newton. So the reading will be less. Your apparent weight will be less than your true weight, right? So it's like your mass will be 77 kilograms instead of 100 kilograms. So you weigh less. Okay, so that means instead of having 1000, you're gonna read 766. So it has decreased by, no, sorry, 1000 minus 766 divided by 1000. It has decreased by 20% a bit, about, right? So the answer here is 20% less. Oh, and I wanted to show you a simulation here. You see if you include here, you see it's not moving because you have static friction. And then as you increase the angle here, static friction is gonna have to increase until it reaches a maximum, and then you have kinetic friction. So the next one is classic in physics. So you have a string between block A and block B. So block B is 2 kilogram and this is 5 kilogram. And here you have a string, right? So, and you see there is a net force to the right. So apply to the system here. So there will be an acceleration. So they want you to find the tension, right? So it means the force that A apply to B. So you see B has to pull A. And according to Newton's third law, A has to pull B. So that also answers one question here. There has to be the same force A on B and B on A. Now you see that F has to pull both B and A. That force here is only pulling A. But everything here has the same acceleration. So if I was to be able to put a little scale here, okay, like little scale, the force will be the same. It's a string, the force is the same. We suppose that the string cannot be stretched. Now, the key here, when you have multiple components in a system, is to choose your system wisely. So we want to find T. Okay, so I could take that system here, only this system here, and I have T, but I do not have A. So the first step is always to take, so I call that a bag, to put everything inside that bag, and you look at what are the forces acting on that bag, right? So you have a bag, you don't know what is inside the bag, you don't know the forces. So inside the bag, of course, you're going to have T to the right and T to the left, but it doesn't matter, they're going to kill each other. And now your bag has a mass of 7 kilograms. Okay, and the force applied will be the pull here. Of course, it's going to have a weight, and of course, it has a normal force. And now I can apply Newton's second law. So the force equals the mass is 7 times the acceleration. So the acceleration will be so the acceleration will be 50 divided by 7, which is about 7 something. 7 times 7 is 49. So let's say 50 divided by 7. So let's keep 2 digits after the period 7.14 meter per second per second. Okay, so once I have done that, I can focus, for example, only on this here, on the system A. So if I do, so I take my block here. Second step, I'm going to focus only. I'm going to open, so in my bag now, I'm going to just put this here. So now in my bag, in my system here, the mass is 4 and the force applied is that T here that I'm trying to find. See, so that T has to pull 5 kilograms. Of course, there will be so that will be a 5G and it has a normal force, I don't know, N prime, for example, but we do not care. Right, so I can apply again Newton's second law. So I say the tension, and of course it has the same acceleration, obviously. So this one is not moving faster than that one, and they all move at the same rate, and they accelerate, and they move faster with the same rate. So the tension will be the mass, which is 5 times 7.14, and I get 35.71 Newton. Significant numbers, maybe 2 or maybe 1, or let's say 2. So it's going to be 36 Newton. Okay. Now, I could instead use this system, this one, right? I could instead take this one here. So instead, I could have used this system here. So that will be my bag here. So in that case, you will have, so that was a force. So here you have the weight, 2 times G. You have another normal force, because normal force depends on the weight, and you have a tension T here. So if I use this one, I see that the force, so 50, minus the tension, so 35.71, equals the mass, so 2 times, no, sorry, we want to find T, right? So let's see. Oh, you can check for the acceleration. Otherwise, let's say you want to find T, 2 times 7.14. So T equals 50 minus 2 times 7.14. And you get the same thing, right? So 50 minus 7.14 times 2, about 75.7. Okay, and it depends. So if you have just, you can say 30, about 35. So about, the answer is about 36 Newton. Now, if you have friction, it makes things a little bit more complicated, because then the frictional force here, so it's exterior force. So you see if you have a frictional force for this one and a frictional force for that one. So more frictional force here than you have there, because it depends on the normal force, or how hard it's pushing in. So if you look at the frictional force here, so if you go back here, you see frictional force here will be 0.1 times the normal force equals to the weight. The weight is 70, right? So if G equals 10, the weight will be mass times G. So 7 times 10 is 70 Newton. So the frictional force will be 0.1, the coefficient, times the 70. So the frictional force will be 7 Newton. So from here, you can find the acceleration. So you can say 50 minus 7 equals the mass, 7 times the acceleration. So you find the acceleration, and then you look at each, you can look at this one, for example, and you will say, okay, the frictional force will be 0.1 times 50, so that will be 5. You have the acceleration, so you can find the, I don't know if I should do it or not, but you understand how it works. I cannot erase this. So now if you have a frictional force will be in this direction. So you have, so first of all, what is A? So A will be 50. So it will be 50 minus frictional force is 0.1 times the weight, which is 70. So this, okay, divided by the weight, no, the mass, sorry. So it's going to be 6.14. So it's less than before, right? 6.14. Before it was 7.14. Then you are just looking for this system here. So you have T, okay, the pulling force minus the frictional force 0.1 times the weight, which is, the weight is 50, equals the mass 5 times 6.14. And you can find T. Okay? I'll let you do that. But that was more challenging. If there is something for the test, I won't make that challenging. It's not that challenging anyway. So this one is also a classic one. It's a conical pendulum. So this picture, I took it from your book. So again, the textbook is University Physics. Okay, and you can see in real life what could be a conical pendulum. So there is a mass here. You have a string and it's gonna go in a circle, and we neglect friction, so it keep going around just by inertia. Okay, it's keep going in a circle. Okay, and here I have some numbers for you, and here I have some questions. So first of all, you let's look at the forces acting. So first we define the system. So the system will be this mass. So of course there is the weight pulling down, and the only other force would be the tension in the string, right? The tension in the string. And then the question is, where is my X and Y axis? Should I take it here so the Y axis is along the tension, or should I take it this way, right? Like a cross. So when you have a circular motion like this, you always want to choose your X-axis along the R here. So that will be your X-axis here. Okay, so that's your X-axis if I do it properly. Okay, X-axis here. And then you want to do, it could be, you can take the plus here, the minus there. But on the Y-axis, of course, it's going to be perpendicular to it, right? So that's going to be your Y-axis. So each time you have a circular motion, always take the X-axis in the plane here of the motion along parallel to the radius. Okay? So now you see that the tension has two components. So it has a Y component along the Y axis, okay? And these components will be in charge of balancing out the weight. And then you have a X component, which is not balanced out, because this component here is what keep the mass on a circular path. It's what keep the it's because of this component that mass here does not go off track. Okay, so it stays on the path here, on the circular path. So that's what we call in physics the centripetal force. If there was no such force, off tangent it will go. Okay, so in a circular motion, you always take the x-axis here along the r, and of course, the acceleration will be the centripetal acceleration, and centripetal meaning toward the center. Okay, so we can decide to take this way to be plus, this way to be minus. Okay, always in the same direction as the acceleration. So the centripetal acceleration is provided by the x component of the tension, and it's equals to v squared mv squared over r. Okay, so this is the scalar. That will be the magnitude. Okay? Now, you can write along the y-axis. So then Newton's second law, it's easy. It's not, there is no acceleration here. Both forces balance out. So we can say that the y component of the tension equals the weight. So this angle here is 5 degrees. We're going to have it here. And you see this is parallel to that. So you're going to have that angle here. 5 degrees. And this is 5 degrees, right? So it's going to be t. So the y component, you want to have a cosine beta equals mg. So that will be equation 1, say. Equation 2 is along the x-axis. So you're going to have that the x component is not balanced out by anything. It's going to provide the centripetal force. You always have something, a force to keep the object on the path, on the circular path. So that will be that x component. So you're going to have sine beta equals mv squared over r. Okay, so now let's look at the equation. So find the tension. Okay, so if I want to find the tension, I can use these equations, right? So we have from equation 1, the tension will be mg cosine beta. And so if you take your ti, so the mass is 80, and then I'm going to take 9.81 for g, and then divide by cosine 5. So it's going to be about 788. Okay, so the mass is 80 times 9.1. So let's do it again. So 80 times 9.81. Okay, and you divide by cosine 5. Okay, and you get about 788 Newton. So that will be the answer for equation A. Okay, so you see 788 Newton, that's how much is along this x-axis. Then B, find the speed. So the speed, you have different ways to do it. You could, for example, you could use equation 2. That's one way. Okay, you can use equation 2. Okay, so you see that v squared equals the radius t sine beta over m. That's one way. Or let's do it a different way. You have a sine here and you have a cosine there. So sine and cosine, you know that sine over cosine, it's going to be the tangent. So that's a different way to do it. Okay, so we want to do equation 2 over equation 1. So it's going to give us t sine beta over t cosine beta equals, that's going to be this here, mv squared over r times, you divide by this one, so 1 over mg, So this cross out, which is equals to V squared over RG. You can go. Okay, so then we get tan beta equals V squared over RG. So V squared equals tan beta RG, and then you can solve for the speed. So in the lab, you can use this equation here. You can find the speed, and once you have the speed, you can find the period. Okay, so then you just have to plug it in. So first you need to find R. Okay, and we know this is a triangle, right angle triangle. So we have sine beta equals R over L. So R will be sine beta times L. So let's see how much you get. L is 10 times sine 5 degrees, which is very small. So we get about 0. Okay, so that speed, it's going to be about 87 centimeter. So you plug it in, you go from here to there. So that's going to be V equals, and then take the square root, and then you have R, and then you have G. So you can just plug it in. So square root of, you have tan, so tan is here, 5 times R, which is 0.87 times 9.81, so 0.86 about. It's a very small speed, 86 centimeter per second, so that will be the speed. And then find the period. Okay, so the period, you see that the speed is 2 pi r over the time. Okay, so you can use this equation. I'm running out of space. 2 pi r over the speed. So if I take my calculator, that's going to be 2, and then a pi, and then r, which is 0.87. So that will be the distance around. Divide by the speed 0.86. You get about 6.35 seconds, about 6 seconds to go around. Okay, so in the lab, you will find the speed, and you will find, the period, and from the period, you can find the speed, and you can check everything else. So then find the algebraic expression between the speed, the angle, and G. We already find that here, right? You have that tan beta equals V squared over RG. So that will be for D. I hope it was not too confusing. Hi guys, so this one is the elevator problem. It's also a classic one. And it's also coming from your textbook, University Physics by Young and Friedman. Okay, so this one is the part A, and you can read. It's very important to understand what's going on. Okay, and so you see here you have the mass here of the elevator, and it says it was going down with a velocity of 10 meters per second. So this is just the magnitude going down here, and then it's going to slow down. Okay, so it's slowing down, and here it stopped. So V final here equals 0. So it's moving down. So if it's gonna slow down, the first thing you need to understand is that which way the acceleration is pointing to. So remember that the acceleration is always proportional to the net force. So that means not only it's proportional in magnitude, but they both have the same direction. So if it's slowing down, that means here the net force will be in this direction. Okay, the net force. So that means here is the tension, okay, that will make that, that will provide the acceleration, right? And then down, you still have the weight, but you see that the tension here has to be larger than the weight. So the acceleration, the net force is in this direction. So the acceleration is up, initial velocity is down. So this is very important to set right at the beginning. The other thing you want to know, what is the system? The system is the elevator. So you are looking at this and the mass, the inertia is 800. So this is the most important. Okay, once you have done that, then it's easy. So the other thing that you want to make sure is that positive, okay, is in the same direction as the acceleration. So it will make things easier in all kinds of problems. So up is positive, down is negative. So the first thing they want T. To find T, you need to find the net force. To find the net force, you want to find the acceleration. To find the acceleration, then you can use the kinematics. And it says the distance here. So it means that from here to there, the displacement here, delta x, it's going to be 10 meter, but down. So it's going to be negative. Here, I just write down the magnitude of the vector. Okay, so it means that so the net force, we are doing kinematics. We want to find the acceleration. So you can use the equation V final equals initial plus 2 times the acceleration of times delta x. We have to be careful with the sign. So final is 0. That's going to be 10 squared plus 2 times acceleration times displacement. It's going to be minus 25. I don't know why I said. And now I lost my little eraser. I don't know why it went. Yeah. This is 25. So minus 25. Okay. So you solve for A. So the acceleration will be 100 divided by 2 times 25, parenthesis here. That's going to be 2 meter per second per second. Okay, so the acceleration is in this direction. So the velocity is losing 2 meters per second every second. So it starts at 10, and then it's going to be at 8, and then it's going to be at 6, and so forth and so on. So we do have the acceleration. Then I'm going to use F net equals mass times acceleration. So Newton's second law. And I decide that up is plus and down is minus. So the force here, you have the tension minus the weight equals mass times acceleration. So the tension equals mass times A plus G, right? And G, let's say it's 10 to make things easier. So the tension, okay, has to provide the deceleration, but also has to fight against gravity. So that's why you have a plus here. So it's going to be 800. And then here it's going to be 2. Is it a 2? 2. The mass is 800. Oh, no, it's 800, right? Mass is 800. The mass 2 is the acceleration plus 10. So that's going to be 800 times 12 Newton. Okay, so it's the mass 800, and then the acceleration, you have the acceleration due to gravity plus the acceleration here, which is 9600 Newton. Okay, but that's not done. There is another question. With now in this elevator, okay, we have a lady now inside. I don't know. Okay, so we're gonna put a lady inside. Okay, so now we have a lady inside. So now our system, it's not the elevator, it's gonna be the lady. Okay, so we focus on this. That's gonna be my system. That's what I have in my bag, if you. So, and she's standing on, let's put a bathroom scale here. They want to know the here. That's the question. So the lady is inside. We know its initial its mass. The mass is 50. The mass is 50. What's going to be the reading on the bathroom scale? So when you see bathroom scale, that means find the normal force. N. Okay, or normal force, it's like the support force. We can call that the support force. That means find the apparent weight. Because you know, when you're gonna be in an elevator and the elevator is slowing down, you get to the first floor, you feel heavier, right? So the apparent weight will be heavier because your body keep going down. The elevator is slowing down, but your body wants to keep going at the same speed. So your body is pushing more on the bathroom scale. So bathroom scale is pushing more on you. So same idea here. The force acting on the lady will be the normal force and the weight. Normal force goes from the ground to the system. And you see that the normal force has to be greater than the weight because you are slowing down. You want to have the net force up. Okay, so now I can apply Newton's second law again. So the normal force minus the weight equals mass of the lady times acceleration. The acceleration is 2, and we take up to be positive. So the normal force will be M A plus G. So the lady is going to feel heavier. So the mass of the lady is 50. That's going to be a 10 plus acceleration is 2. So it's going to be 50 times 12. Okay, so 50 times 12, I think it's 600. So 50 times 12, 600 Newton. So that will be the apparent weight. The true weight is 500 Newton. Okay, so she's feeling heavier, okay, by 100 Newton, okay, which is her real weight is 500, and now she's heavier by 100 Newton. So that's going to be 20% increase in apparent weight, right? So the apparent weight will be 20% more than her true weight. Okay. And then there is a next question. What's going to happen if now the doesn't want to erase now? Cannot erase. Not sure why. So the next question is, I can write here and I cannot erase. I can erase this, but I cannot erase that. So next question will be, what's going to be the, if the acceleration is now up? So now the question is, what is the reading if the acceleration is now, if the elevator is accelerating down? Okay. So what's going to happen? So now we still have the lady inside. Okay. But now the acceleration is down with a 2 meter per second. So what I'm going to do, I'm going to take, since this is the acceleration and this is down, I'm going to take down to be positive because it's good. It simplifies things if you always take the acceleration to be positive. So you can decide of positive direction as you want. So it means that her weight, so the weight is still down, but it has to be larger than the normal force. And you know that you're going to feel lighter, right? Now we can apply Newton's second law. So mg minus the normal force equals the mass times the acceleration. So the normal force, which is the apparent weight, will be m times g minus a. So now the normal force will be equals to 80. Yes, 80. No, it's not 80, it's 50. 50 is the mass, yes, times 10 minus 2. So we have 50 times 8, of course, it's going to be 400 Newton. Okay, so she lost 20% of her weight in this case. Okay, so this is also a very classic. Okay, so that's going to be the next one. And you're going to have one problem like this. So it's an equilibrium situation. So the question is, so you know this is 100 kilogram. Okay, and it's in equilibrium. So that means T1. So it's a vector sum. T1 plus T2 plus T3 equals 0 if you consider this system here. Okay? So I'm going to consider this system here. So let's see what's going on. You always have to define the system that you are working on. Okay, so if you are working on this system here, which is a massless ring, okay, so you're gonna have T1 pulling down. So T1 is gonna be down. And then T3 gonna have T3 here. T3. And you have T2 pulling in this direction. So that will be for this system here. And if you take that system here, so if you just take the motor or engine, if you take the engine only here, so in that case, the engine also is in equilibrium. So you're going to have the weight here, mg, and then force up is going to be T1, right? Because if the string is massless and it cannot be stretched, so it will be the same force that is transferred through. Okay, so it's the weight of the motor that is pulling on the string. It also makes sense. Okay, so let's look at the equation. So first of all, you can make your x-axis, and here you have your y-axis. So we are back to this string. So remember, it's always good to I cannot erase anymore. It's always good to visualize the components of the forces along the axis. So how much is T3 along the x-axis? That's going to be how much? So Tx. And then along the y-axis, you go from tail to head. So that will be the y component. So that's going to be the y component. Okay, so this component here is in charge of balancing out T2, and this component here is in charge of balancing T1. They are independent from each other. And what about the angle here? So you're going to have 60 degrees here. So that means that's going to be 60 degrees, and that's going to be 30 degrees, right? So if you have two parallel lines, that angle here, it's going to be the same as this one. So from this system here, my first equation, I'm going to have that T1 equals mg, or up equals down. So the mass, if I take g equals 10 meter per second, so that's going to be 1000 Newton. Okay, and then second equation, I'm going to look along the x-axis. You see that left equals right. So left is going to be T2. Right, it's going to be T3x, which is T3 cosine 60. Okay, so x component is always cosine if you are given this angle here with the positive x-axis. So third equation, you have up equals down. So up will be whatever you have along the y-axis, which is the y component of T3 equals down you have T1. So you have T3 sine 60 equals T1. Okay, so from the third equation, you have T3 equals, so 1000 divided by sine 60. That's going to be 1155 Newton. So you can double check that. Okay. And then you go back to equation 2. So from equation 2, you have T2 equals T3 cosine 60. So it's going to be 1155 cosine 60, and you get about 561 Newton. So as long as you take the components, it's not that hard. So let's move to the next one, which is not hard. So the mass, so you have like a mass here. It's a sled, which is 25 kilogram, and it's going into a circular motion. And there is no friction because it's ice. Okay, so it has a speed here. So here we have a velocity. So it wants to keep going in straight line at a constant speed, but it can't because there is a force here pulling toward the center, and that will be the centripetal force. Okay, so what is given? The mass is 25 kilograms, and then the radius is 5 meters. So this is 5 meters. Okay, and it's doing 5 revolution. So 5 revolution per minute. So you have, I'm going to show you 2 ways to do it. So first of all, one way is just to say, okay, the centripetal force equals mv squared over r, and we can find the speed here. So 1 revolution is a distance around. Okay, so this is 1 revolution. So if I want to convert that to meter, I will do 2 pi r. Okay, the time, 1 minute, is 60 seconds. So the speed is the distance divided by the time. That will be in meters, that will be in seconds. So it's going to be 5 revolutions, so 5 times 2 pi r divided by 60. Right? So you get a speed of about, you plug that into your calculator, it's going to be about 2.62, and you keep all this decimal until we finish the computation. So then the force will be the mass, which is 25 times 2.62 with all the decimal here, square over the radius, which is 5. Right? And if you do that, you can pause the video. You should find something like 34 Newton. So let's see. It has 3 significant figures. So okay, we can keep 34 Newton. You can even add 1 more digit. Now, the other way to do it could be like F equals M. So you know that the speed is 2 pi r over the time for 1 revolution. So it's going to be, you have to square it. So it's going to be 4 pi squared r squared. And then here you have a r, and then here you have a t squared. So you can cross this out. So the time for 1 revolution. So you see that 5 revolution is for 60 seconds. So 1 revolution, you divide by 5, so that will be 12 seconds. So that's going to be 25 times 4 pi squared times 5 times 12 squared. Right? So that's a different way to do it. Not a different way, but it's more elegant, shall we say. and you get about the same thing. Okay, so let's do this one. So that comes from your book. It's the end of chapter problem. So it's university physics. And so let's do, it's also very typical problem here. It's a variation of what we did in class. Okay, so the first question, so the system is moving and it's moving at a constant speed. So that means there is no acceleration and there is kinetic friction between A and the table here. So one way to do those kinds of problems is to consider like the system will be everything here. Okay, it's like one way to do it. It's a multiple component system. So it's like one bag here. And what are the forces acting on this bag here? So here, that will be the driving force. That will be the weight. Okay. And the force opposing this motion here, so it doesn't fall, it's not in free fall, will be the kinetic friction here between A and the table. So that will be what's going on here. That's what you're going to use for Newton's second law. Of course, you also have the weight here and the normal force, but they cancel each other, right? Up equals down. So what matters is the net force will be this minus that. So in that case, it's in equilibrium because A equals 0. Okay, so let's write down Newton's second law. So the driving force, the winning force here is the weight minus the kinetic friction, the kinetic friction, yes, equals the total mass, so mb plus ma times the acceleration. So if you were asked to find the acceleration, you use this equation. But in that case, you know that the equation equals 0. Okay. So that into here, you get that the weight minus the kinetic friction equals 0. Second equation, you know that the kinetic friction equals the coefficient times the normal force. Okay, and third equation, you know that up equals down, so the normal force equals the weight of A. Okay, so 3 into 2, you see that the kinetic friction equals the coefficient times the weight of A. Okay, so let's go back to first equation. So first equation, you see that the kinetic friction, okay, the frictional force equals the weight of B, and B, the weight of B is 45 Newton. B is, no, B is 25 Newton. So it's going to be 25 Newton. Okay, so that equation here into 2, you see that the kinetic frictional force 25 equals the coefficient mu k times the normal force. So I use also equation 3, okay, times the normal force, and the normal force equals to the weight of A, which is 45. Okay, so if you do that, it's going to be 25 over 45. And it's gonna be 25 divided by 45, 0.0556. So you have 1, 2, 3 significant figures. So I can keep 3 here. So number 2, so the things is going down. So it's moving down. Okay, so it's in motion at a constant speed. All of a sudden, here you have a cat. It says there is a cat. And the cat is falling. I don't know how it can happen, but maybe Alice's cat is falling on that block here. Okay. So of course it's going to increase the weight. And so it's going to increase the normal force. So it's going to increase the frictional force, right? Because you are pushing more onto it and it was moving. So to understand what's going on, remember it's moving. Okay, so obviously what's going to happen is going to slow down because it was moving to begin with. And all of a sudden, you see you have a frictional force here that will increase significantly more than that force here. So it's going to slow down. Because already it was at the limit, right? It was moving at a constant speed. It was not accelerating down. So if you increase here the weight, you're going to increase the frictional force. So it's going to slow down. Okay, so we have to review all the equation. So first equation, A here is not equals to 0. So A is not equals to 0. I want black. Okay, not equals to 0. So the weight here, okay, so let's, I don't know if I can erase everything. Okay, so that equation here is not 0. So you still have the driving force here, the winning force, which is the weight of B, which is 25. So we have 25 minus the frictional force, but the frictional force will be the coefficient times the normal here, right? Normal on A equals, now I'm considering the system including the cat. So in my system now, I have a cat in the bag. Okay, so now I have more mass. I have the mass of B, which is 2.5 plus 4.5 plus the mass of the cat plus 4.5a. And I take gravity to be 10 meters per second per second. The acceleration here is in this direction. So I take plus in this direction. Plus, minus, plus, minus. Okay, so we need to find, we have that. We know that the coefficient is 0.556. So we need to find that normal force. Up equals down. So that normal force equals the weight of the cat and the weight of the block, which is 90. Okay, so I can apply 2 into 1. So I have 25 minus 0.55690 equals total mass is 9, 10, 11, so 11.5 times the acceleration. Okay, so you have 25 minus 0.556 times 90. Okay, divide by 11.5, which is minus and so this comes from your book, and that it is if you use G equals 10. So that's one way to solve a problem. Another way to solve a problem is to focus on B and then to focus on A and to say that they have both the same acceleration. That's a different way to do it. So this one is also classic. It's a circular motion. Each time you have a circular motion, you need a net force, okay, equals mv squared over r. And you need to have a net force that will be pointing toward the center. So in that case, it's going around. We have the mass. So we have the weight, we have the radius, and at the top here, it says the normal force is 6 Newton in magnitude. So first of all, let's draw the vectors here at the top. So the normal force is always from the surface or the ground or the track to the system. The system is the car. So the normal force is going to go pointing down. So that's going to be your normal force here. And of course, the weight is down. So we have two forces that are pointing toward the center and that will provide the centripetal force, right? So we're going to have the normal plus the weight equals mass times acceleration. So from that equation, you can solve for the speed, okay? Or you can keep the acceleration, because the acceleration, if it's moving at a constant speed, it's going to be the same when it's at the bottom. You see, the centripetal acceleration is v squared over r. The speed stays the same, r stays the same, so the centripetal acceleration is going to stay the same. So this is 6 plus the weight is 8. The mass is 0.8 times the acceleration. Okay, so we have an acceleration of 6 plus 8, 14, divided by 0.8, so 17.5. So acceleration is 17.5. Now you can use that to find the velocity, but they don't ask you that, or the speed. Okay. Then they ask you what is the normal force at the bottom. So at the bottom, you see, still the normal force always go from the track or the surface to the system. So N, it's going to be here. But it has to be larger than the weight. The weight is down. Okay, so because it has to provide the centripetal acceleration. And we always take toward the center to be positive, right? So when we're going to do Newton's second law, toward the center is always positive because the acceleration will be in this direction. So we have N minus mg, so that will be your net force, equals mass times acceleration. That will be n prime. So n prime equals mass times acceleration plus mg. So that's going to be the same as that, right? Or you can do mass times AC plus G. Okay, so it's same, right? So the mass is 0.8, and then you add 17.5 plus 10. So it's about 22 Newton. It's about 22 Newton if G equals 10. So what I might ask you is to draw these vectors. So this one is larger here, but it's pointing toward the center. It depends on the situation. So for example, if you have a situation like this, so here it's not the same, right? So it's also a circular motion. But you see, the normal force in that case is so the system is, let's say it's the lady here. I don't know if it's a lady. I mean, it's the person here. So you go always from the surface to the person. So N is going to be this way and mg is going to be that way. So that means that the normal force, okay, or mg, so if down is positive, so down, the acceleration is down, so this is positive, this is negative. So in that case, you have that mg minus m equals mass times acceleration. So that normal force is the apparent weight. So it means when you are sitting on that chair, you feel like in your stomach, right? You feel very light. It's like if there was no seat belt, off you can go, right? You can leave your chair. Whereas when you go down, okay, so it's moving this way, now you have a normal force from the chair to you. That's going to be the normal force. It has to be larger than the weight, mg. Okay, so up is plus, down is minus. So now we have normal force minus mg equals mass times acceleration. So now you're going to feel heavier, right? You're going to feel heavier in your stomach. Okay, but the answer for that question was, it was this. Okay, I think we are done.